Hello, am I audible? Okay. Hello, am I audible? Hello, welcome to Goscore Learning, the fastest growing edtech industry in the Middle East. I'm your Dhanya ma'am with your fourth part of solution chapter. In the previous part, we have already discussed regarding the colligative properties, that is, the relative lowering of vapor pressure, depression in the freezing point, elevation in boiling point, and the osmotic pressure. I think the colligative properties portion is clear for everyone. Today, in the part 4 video, we are going to discuss about the osmosis, reverse osmosis, and about the abnormal molar mass and Van Hoff factor. With that, we will finish this particular chapter today. So, are you all ready? Can we start the session? Okay. So, before entering into the topic, we can just have a discussion on the colligative properties. That is, those properties which depends upon the amount of substance and not on the nature of substance. Those kind of properties are what we call colligative properties, and the main colligative properties are relative lowering of vapor pressure, elevation of boiling point, depression in freezing point, and osmotic pressure. So what was the expression that we used, that we learned in the last part about the relative lowering of vapor pressure? It is delta P upon P naught is equal to mole fraction of solute, right? That's equal to number of moles of solute divided by mole fraction of solute means number of moles of solute divided by number of moles of solute plus number of moles of solvent, right? For very dilute solution, what we can write? We can just ignore the number of moles of solute in the denominator and we can write number of moles of solute upon number of moles of solvent. That is only for very dilute solutions. Okay. And moving on to the elevation of boiling point, what the expression we learnt? That is delta TB. Boiling point, changes in the boiling point is equal to what? KB into M, where M is nothing but the molality. M is molality. What is the expression? How we will find out the molality? Molality is number of moles of solute, divided by this is molality, so it will be mass of solvent in kilogram, right? That's how we will find out the molality of solution, and the change in the boiling point is delta TB is equal to KB into M. What is this KB? KB is nothing but the molar elevation constant, or it is also known as ebullioscopic constant, right? And this value will be different for each solvent. Okay. And what about the depression of freezing point? Depression in freezing point, that is given by delta TF is equal to KF into M, where M is nothing but the molality and KF is called the freezing point depression constant, or is also known as cryoscopic constant, right? And what about the same one? The M is nothing but the molality. And finally, about the osmotic pressure. Okay, so what is the expression for osmotic pressure? It is pi is equal to CRT, where C is nothing but the molarity. See, for elevation, boiling point and depression and freezing point, we are using the molality. And for osmotic pressure, here we are using molarity. What is the formula for molarity? Molarity is nothing but number of moles of solute, divided by volume of solution in liter, right? So here C is nothing but the molarity and R is the gas constant and T is the temperature in Kelvin. Okay, so these are the expressions that we learned in the previous part. So I hope it is clear. So today we are discussing about the reverse osmosis. Before that, I just want to give you an introduction about the osmosis. Okay, see, osmosis. So, what do you mean by osmosis? For explaining the osmosis, here I have taken a container and I have separated the container by using a I have separated the container by using a semi-permeable membrane. What it is? Semi-permeable membrane. What do you mean by semi-permeable membrane? Semi-permeable membrane is nothing but it will allow the passage of only selected particle. From the word itself, it's clear. Semi-permeable. It allow the passage of certain particles only. Okay, it won't allow the passage of all the particles. Only selected particles can pass through this membrane, and that type of membranes are what we call the semi-permeable membrane. Okay, so in the one section of this semi-permeable membrane, I have taken the pure solvent. Okay, so this is our pure solvent. Okay, so this is the pure solvent, and here I have taken the solution. This is the solution. So in solution, definitely there should be some solutes, right? So this is the solution part. So we can mark it as this is solution, right? So we have separated the pure solvent and solution by using a semi-permeable membrane. Now see, when you kept solution like this separated by a semi-permeable membrane, the solvent will move from the pure solvent side to the solution side. Okay, only the solvent can move through the semi-permeable membrane and it will move from the pure solvent side to the solution side. Okay, so just listen here. Pure solvent means its concentration is less. There is no more solutes, right? So it's a low concentrated solution, right? So this is a low concentration. This side is low concentration. This side is high concentration, right? So what we can say in terms of concentration, the movement of solvent from a low concentration to a region of high concentration through a semi-permeable membrane. That passage of solvent from pure solvent to solution side or from low concentration area to high concentration area through a semi-permeable membrane is what we call osmosis. Okay? Osmosis is passage of solvent molecule from pure solvent side to solution side or from the low concentration to higher concentration through a semi-permeable membrane is what we called osmosis. Okay, so when this water is moving, solvent is moving from this area to this side, definitely it will cause a hydrostatic pressure there, right? So this flow of solvent will continue until the equilibrium is reached. So the flow of solvent will continue until the equilibrium is reached. And if you are applying an external pressure, so from this side, if you are applying an external pressure, that pressure, so the flow of solvent is like this, it is exerting a hydrostatic pressure on the solution side, and you are applying an external pressure. That external pressure, when equal to this force, what will happen? It will stop the osmosis, right? That external pressure which will stop the flow of solvent from solvent to solution through the semi-permeable membrane is what we call osmotic pressure. The external pressure which will stop the flow of solvent through the semi-permeable membrane, or which will stop the process of osmosis, is called a osmotic pressure. Done. So this is clear for you, right? So usually in osmosis, the solvent flows from a low concentration solution to low concentration area to higher concentration area through a semi-permeable membrane, or from a pure solvent to solution through the semi-permeable membrane. And the external pressure which will stop the flow of the solvent is called osmotic pressure. Okay, and this osmotic pressure we are representing with. Okay, now see, what do you mean by reverse osmosis? Okay, here we have taken the solution and we have applied, see, here we have taken the solution and we have applied an external pressure, right? So, if the pressure applied here, this was in equilibrium, the flow of solvent was like this. I have applied an external pressure just to stop the osmosis process, right? If this applied external pressure is greater than the osmotic pressure, if this is strong enough, greater than the osmotic pressure, what will happen? It will pull like this, right? That means this is stronger than the osmotic pressure. The reverse osmosis process will occur, right? See, here we have taken the solution separate, two solutions separated by the semi-permeable membrane, and here we have taken the solvent, and here in the side we have taken the solution. So the osmosis will occur from the solvent side to the solution side, right? This is what osmosis. So from here we are applying a pressure. When this pressure is equal to osmotic pressure, what will happen? The process of osmosis will stop, right? The process of flow of the solvent will stop. If the applied pressure P1 is greater than the osmotic pressure. If the applying pressure is greater than the osmotic pressure, what will happen? The reverse process will occur. That means the solvent will flow from the solution side to the solvent side. That means from a higher concentration region to higher concentration to lower concentration. Okay? When you apply a pressure greater than the osmotic pressure, the solvent will move in the opposite direction of osmosis. That is from the solution to solvent through the semi-permeable membrane. This is the semi-permeable membrane, or from higher concentration to lower concentration through the semi-permeable membrane. This is what we call reverse osmosis. Because here the osmotic pressure, the pressure we are applying is greater than the osmotic pressure. That is, the pressure applied is greater than pressure required to stop the flow. So what will happen if the pressure is more? It means the process will occur in reverse direction. That is what the reverse osmosis, and the main application of this reverse osmosis is for the purification of seawater. So for that we will take the pure water this side, and this side we will take the seawater. That will contain impurities. Mark it with another color. That will contain impurities also, right? So what will happen is, if you are applying a pressure on the solution side that is greater than the osmotic pressure, the solvent particle from this is the seawater, right? This is the pure water. So if you are applying a pressure that is greater than the osmotic pressure, what will happen? The solvent from this solution will move to the pure solvent side. That the solvent will move from the higher concentration to lower concentration area. Okay. So thereby we will get this is a semi-permeable membrane which will allow the passage of only the solvent molecule. So all the impurities will be there in the right side, and only the solvent will come into the pure solvent side. Thereby we can purify the seawater. That means only the water portion, that is the pure solvent portion, will come through the semi-permeable membrane. Thereby we will be getting the RO water, that is reverse osmosis water, purified water. We can purify the seawater by this reverse osmosis process. I think it's clear for you. Now we can discuss about the isotonic, hypertonic and hypotonic solution. See, here in a container, I have separated the container with a semi-permeable membrane. Okay, and in this side, I have taken a solution which is having the osmotic pressure by A. Okay, in this side, I have taken another solution which is having the osmotic pressure by B. Okay, now see, if the two solutions that are separated with the semi-permeable membrane are having the same osmotic pressure, if pi A is equal to pi B, then these type of solutions are called isotonic. The solutions which have two solutions having same osmotic pressure at a given temperature is what we call isotonic solutions. Isotonic solutions are two solutions that have the same osmotic pressure at a given temperature is what we call isotonic solutions. Okay. Now see, in our body there will be RBC, right? In the RBC, the fluid in the RBC, that is the fluid present inside the blood cells having the osmotic pressure. Let's see, it will be the osmotic pressure of fluid. Okay, the osmotic pressure of the fluid inside the RBC is isotonic with the 0.9% weight by volume of sodium chloride. That means if you took 0.9%, if you take a concentration of 0.9% weight by volume of sodium chloride solution, it will exert an osmotic pressure that is same to the osmotic pressure exerted by the fluid inside the blood cells. Okay. So, if you are injecting any solutions into the body fluid, it should be isotonic with the fluid in the RBC. Okay, now see why it is important to maintain the isotonicity. So I hope the isotonic solutions is clear for you. The two solutions that having the same osmotic pressure at the given temperature is what we call isotonic solutions, and the osmotic pressure associated with the fluid inside the blood cells. Okay, the osmotic pressure associated with the fluid inside the blood cell is equal to that of a 0.9 percentage. Keep in mind the concentration, it is 0.9 percentage weight by volume of sodium chloride solution. Okay, now we can explain this hypertonic and isotonic in detail. See, here imagine we have taken the 3 containers. Okay, we have 3 containers. Okay, in each container I have filled with the sodium chloride solutions. Okay, this is filled with the sodium chloride solution. This is also filled with the sodium chloride solution. This one also is filled with the sodium chloride solution, right? So here in the mid one, let's imagine here what the solution I have taken is 0.9 percentage weight by volume solution of NaCl. Okay, the concentration of the sodium chloride in the middle beaker, mid one, is 0.9 percentage weight by volume. In the first beaker, I have taken the concentration of sodium chloride which is greater than 0.9 percentage weight by volume of sodium chloride. Okay, so here the concentration of solution, the solution concentration is greater than 0.9 percentage weight by volume. Here what I took is less than 0.9 percentage weight by volume. Okay, so this is the concentration is greater than 0.9 percentage. This is 0.9 percentage. This is less than 0.9 percentage. Now see, if we are putting a RBC cell inside each of this container, see what will happen. Yeah, I am putting a blood cell inside the container. Okay, so in the RBC cell there will be fluid inside it, right? There will be fluid inside it. So this blood cells, the RBC cell will act as a semi-permeable membrane. See what we discussed in the previous session. The fluid, the osmotic pressure exerted by the fluid inside the RBC is equivalent to 0.9 percentage. The osmotic pressure exerted by 0.9 percentage weight by volume of sodium chloride, right? So this osmotic pressure of this solution is equivalent to osmotic pressure exerted by 0.9 percentage weight by volume of sodium chloride, right? So what it is? This is an isotonic solution because the osmotic pressure exerted by the fluid inside the blood cells is equivalent to the osmotic pressure exerted by 0.9 percentage weight by volume of sodium chloride solution. So since the osmotic pressure of both the liquids are same, it's an isotonic solution, right? Now, see here. Here the concentration of the sodium chloride solution is more, right? The solution what we took is greater than 0.9 percentage. So here this will be higher concentrated solution compared to this one, right? This will be low concentration solution. So what will happen when you kept this RBC in a higher concentrated solution? Because the solvent will move from the cell into the solution, right? The solvent will move from solution cell inside the fluid inside the cell will starts to move out of the solution through the cell membrane. Then ultimately what will happen if all the water inside the cell is coming out? The cell will shrink, right? The cell starts to shrink. So, this type of solutions that having concentration greater than 0.9 percentage weight by volume of solution which causes this RBC cell to shrink is called hypertonic solutions. Okay. So, hypertonic means the word hyper means the concentration is more. So, here the concentration of the solution is more. So, the solvent will move from the cell fluid to the solution. So, that will cause the cell to shrink. That type of solutions are what we call hypertonic solution. Now, see the third case. Here we have the solution having the concentration less than that of 0.9 percentage weight by volume of sodium chloride, right? So, here the fluid inside the cell will be higher concentration, right? And the solution will be lower concentration. So, what will happen? The solvent will move from the solution side into the cell, right? So, as more solvent get into the cell, it will cause the cell to swell. The cell starts to swell and finally it will burst. These kind of solutions which having the concentration less than the 0.9 percentage weight by volume of sodium chloride is called hypotonic solutions, right? So, isotonic means the fluid, if you are keeping the RBC inside the osmotic pressure exerted by the body fluid inside the cell is equal to the osmotic pressure exerted by the 0.9 percentage weight by volume sodium chloride solution. So, there won't be, as since the two liquids is having the same osmotic pressure, there will be no flow of solvent. That type of solutions are what we call isotonic solution. In the case of solutions having concentration greater than 0.9 percentage weight by volume, if you keep a blood cell inside that, what will happen? The concentration outside the cell is more and the concentration of the fluid inside the cell is less. So, the solvent will starts to move from inside the cell to the outside fluid. That causes the cell to shrink. Okay, that type of solutions having greater concentration is called hypertonic solution. And if the solution is having concentration less than 0.9 percentage weight by volume, what will happen? This solution will have a lower concentration and the fluid inside the RBC will have the higher concentration. So, the water will move from solution into the RBC cell. That causes the cell to swell and finally bursting. Okay, so I hope the isotonic, hypertonic and hypotonic solution is clear for you, right? Okay, now let's see the next term. With that, we finish the osmotic pressure, reverse osmosis, isotonic, hypertonic and hypotonic solution. Now, we are going to discuss another important term, that is the abnormal molar masses. Okay, see, what is actually this abnormal molar mass? We have discussed the colligative properties, that all the colligative properties depends upon the number of particles. Okay, that means the amount of substance present in solution, right? So, of course, all the properties are depending on the amount of substance and we are calculating the colligative property based on the amount of substance, right? So there we have discussed about the urea, glucose, all these are non-electrolyte. That means they won't get dissociate or associate in the solution, right? But what about the cases of electrolytes? Just take the example. If you are dissolving acetic acid, okay? If you are dissolving acetic acid, you have taken the 2 moles of acetic acid, okay? If you are treating in presence of benzene, what will happen is this acetic acid, let's imagine, it will undergo association, okay? See, this acetic acid is CH3, C double bond O, OH, right? That is the 1 mole of acetic acid. See the second one, CH3, C double bond O, OH. When these two particles come closer, there will be a formation of hydrogen bond in between this hydrogen and oxygen. So, see, hydrogen bond is formed in between them and it will form a dimer. See, here 2 moles of acetic acid are there. It get associated to form 1 mole of substance. See, here we will take into consideration 2 mole, right? And we will calculate the colligative property based on 2 moles, right? But actually, inside the solution, what happens? These 2 moles get associated to form 1 mole. So, of course, there is a change in the amount of substance, right? So, the colligative property will also get changed, isn't it? So, what will happen? What the colligative property, what we find out from the theoretical value, it will be different from the practical or the observed colligative value, right? So, there is a change in the molar mass. So, if you take the molar mass here, it is different from that what you get after the association, isn't it? So, there is a change in the molar mass due to association of the molecules, right? So, when there is a change in the molar mass, definitely it will affect the colligative property also. See, if you are calculating the molar mass with the help of the colligative property, if it is different from the theoretical value because of association or dissociation, mainly in cases of the electrolytes, it is called the abnormal molar mass. And the abnormal molar mass is mainly due to association or due to dissociation. So, when the molecular mass calculated with the help of the colligative property, we have done the calculation numericals in the last part to find out the molecular. If we are adding an unknown solute, if the amount of solute is known, we can find out the molecular mass of the solute by using the colligative property. We have done the numericals based on that, right? So, by the way, if you are finding out this molecular mass by the theoretical calculation and you got a value, and after doing the practical session, your the value you got it after the experiment or your observed value is different from the theoretical value, then it is called abnormal molar mass and it arises mainly due to association or dissociation of the particle. Now we can discuss in detail the association and dissociation. Okay, and anyway, we came to know that their association and dissociation is taking place, right? So, in order to express the extent of association and dissociation, we will use the term Van Hoff factor. That is I. Van Hoff factor I. It represents the extent of association or dissociation. So now see, here we have 3 expressions for finding out the Van Hoff factor. That is, Van Hoff factor is represented with the small letter I, and I is equal to normal molar mass divided by the abnormal molar mass. That is the normal molar mass changed due to association or dissociation. So I is equal to normal molar mass upon normal molar mass. And in the terms of colligative property, of course, if the molar mass is changing, it will affect the colligative property, right? So, in terms of colligative property, what we can write, Van Hoff factor I is equal to observed value of colligative property divided by calculated values of colligative properties. In terms of ionization, the number of moles, in terms of not ionization, in terms of number of moles before and after association or dissociation, we can express the Van Hoff factor as total number of moles of particles after association or dissociation divided by number of moles of particles before association or dissociation. You will be getting these things clear if we do the examples. See, here, just take the example. I'm taking the sodium chloride. Okay, see, I have taken the sodium chloride solution. Okay, and just imagine 100% dissociation is occurring. Okay, first we can talk about the dissociation, then we can discuss about the association. Okay, first about the dissociation. So, if 100% dissociation is occurring, what I will get? Na plus and Cl minus ions will form, right? So, in the calculation, what we imagine, there only 1 mole of substance. Based on that only, we will do the calculation. But actually, practically, what is happening there? The sodium chloride dissociated in the solution to form the sodium chloride is in the aqueous form, right? It will dissociated in the aqueous solution to form Na plus ion and a Cl minus ion. So there 1 mole of Na plus and 1 mole of Cl minus. So after dissociation, it changes into 2 moles. Actually, in that solution, there are 2 moles are there. But we are calculating based on the 1 mole. So definitely there will be changes in the colligative properties on the theoretical value as well as in the observed value. That extent is given by the Van Hoff factor. See here, if you consider the Van Hoff factor, I is equal to number of moles after here it is dissociation. So what is the Van Hoff factor in terms of dissociation? See. So here Van Hoff factor will be, what is the total number of moles after dissociation? It is 2. What is the number of moles before dissociation? It is 1. So Van Hoff factor will be 2. And if you take the example of calcium chloride, see, let's imagine here also 100% dissociation occur. Okay. So here how it will form? Calcium Ca2 plus 2 Cl minus it is forming. We will mention the calculation based on 1 mole of calcium chloride. But actually here 1 mole of Ca2 plus and 2 moles of chloride ions are forming. So what is the number of moles of total number of moles after dissociation? It is 3. So what will be the I value? I is equal to total number of moles after dissociation divided by total number of moles before dissociation, that is equal to 3. See, for dissociation, always the Van Hoff factor value will be greater than 1. That is only for dissociation. Okay. For dissociation, always the Van Hoff factor value will be greater than 1. See what we got here? It is 2. Sorry. What we got here, it is 2. What we got here, it is 3. If you take the n number of moles, let's imagine if you are taking AN, the molecule AN, and if it is giving Na, what will be the Van Hoff factor? Okay, sorry. This we can explain for not in the case of 100%. Whatever the things we discussed here, it's for 100% dissociation. But it is not mandatory that all the condition 100% dissociation is taking place, right? So now consider only the equilibrium is reaching, not the 100% is occurring. Okay. So what will be the equation? We can write the sodium chloride is in equilibrium with Na plus and Cl minus. All are in aqueous state, right? Aqueous state, in aqueous state, right? So time t is equal to 0, what it will be? The number of moles of sodium chloride will be 1, right? And 0 time, it is 0, right? There is no more ions formed. It is just the time that we added the sodium chloride, right? Then what will be at equilibrium? Here, 100% dissociation is not occurring, right? Only a fraction of sodium chloride is dissociating. So how we can write it is, it is 1 minus alpha. What is this alpha? Alpha is nothing but the degree of dissociation. Alpha is nothing but the degree of dissociation. So here if 1 mole of get only alpha portion is getting dissociated, what will be the ions you are getting there? Here you will get alpha ion because NaCl, alpha portion of NaCl is dissociating. It will give the alpha Na and alpha chloride. So what will be your I value here? I is equal to, what is the total number of moles after dissociation? This one, hold this, right? These are the total number of moles after dissociation, that is 1 minus alpha plus alpha plus alpha. And what is the total number of moles before dissociation? That is at 0 time. It is 1, right? So what you will get? 1 minus alpha plus alpha, it's get cancelled, and 1 plus alpha by 1, that is 1 plus alpha. So your Van Hoff factor I is equal to 1 plus alpha, right? So this is the case of equilibrium. Same way you can do for calcium chloride also. Just the 2 alpha, it will come there, right? Only the difference is here 1 minus alpha for calcium alpha and 2 chloride ions are forming, it will be 2 alpha, right? So generally what we can say is, generally if you are considering An is in equilibrium with Na, at 0 time there will be 1 mole, and when the time reaches the equilibrium, here 1 minus alpha particle is getting dissociated, and what will be here? N alpha will be forming. So if you find out the Van Hoff factor, it will be I is equal to 1 minus alpha plus N alpha divided by 1. That will be equal to 1 minus alpha into 1 minus N, right? So how can I rewrite it? I'm writing here. I can write it as 1 minus I is equal to alpha into 1 minus N, right? So alpha is equal to 1 minus I divided by 1 minus N. Alpha is equal to 1 minus I divided by, just a moment. We can put it in a bracket. 1 minus I divided by 1 minus N. See, this is the degree of dissociation for n number of moles of particle. Okay, for degree of dissociation, if you want to calculate the alpha, it is equal to 1 minus I is nothing but the Van Hoff factor divided by 1 minus N. N is number of moles of particle, right? So this is in the case of dissociation. Same way we can find out for association also. So I think dissociation is clear for you. For dissociation, always the I value will be greater than 1, and if you consider equilibrium, then there will be not all the particle get dissociated, only certain fraction of particle will be dissociating, and that is what we represent by degree of dissociation. Okay, that is represented by the letter alpha. And for dissociation, for n number of moles of particles, we can use the equation alpha is equal to 1 minus I divided by 1 minus n, where I is the Van Hoff factor, n is the number of moles, alpha is degree of dissociation. So it's clear for dissociation, right? Now we can see for association. For association, dissociation means one is splitting into two, right? So association means two combined to give the one. See, for association, we can take the acetic acid and benzene. Okay. So if you imagine there 100% association is occurring, CH3, C double bond O, OH, here it will form hydrogen bond with OH, it will form bond with double bond O, right? So here 2 moles get converted, get associated to form 1 mole, right? So if you consider if it is in equilibrium, what you can write, just we are considering it in equilibrium. See what will happen here, 1 minus alpha at equilibrium, at initial state it will be 2, right? We are considering for 1, it will be 1, then 1 minus alpha if it is dissociating, here the half portion if it is in equilibrium. If alpha number of particle is getting associated, what will be the product side number of moles you are getting? It will be alpha by 2. Okay. Same way we can do for if it is for Na particle, there will be product will be An, right? So when you consider for one n number of moles, if it is for 1 minus alpha, this will be alpha by n, right? So how we can write the I value? I is equal to what will be the total number of moles? It will be 1 minus alpha plus alpha by n, right? So after doing all the value, we will get the degree of dissociation. In case of association, degree of association value, alpha we will get like n into 1 minus I divided by n minus 1. This is the equation for calculating the degree of association. So if you know this equation, if it is association or dissociation, you could easily find out what is the degree of dissociation. Just want to find out the Van Hoff factor, that you can find out either by using the molar mass or by based on the colligative properties, or by the number of moles dissociation before dissociation and after, number of moles after dissociation or association upon total number of moles before dissociation or association. Okay, you can use the either formula to find out the Van Hoff factor, and if you know the number of moles, you could easily find the degree of dissociation as well as degree of association. Okay, so I think the abnormal molar mass and the degree of association and degree of dissociation, it's clear for you why there is a change in the colligative property when you are adding an electrolyte into the solution or electrolyte into the solvent. Why there is a change in the colligative property, it's clear for you, right? So based on the here for association, what will be the I value? For association, always the Van Hoff factor value will be less than 1. What we discussed for dissociation, always the I value will be greater than 1, and for association, the I value will always be less than 1. Okay, so if you are getting an I value and Hof factor value less than 1, indicate that here there the electrolyte is associating. And if you are getting an Van Hof factor I value greater than 1, it indicates their dissociation is occurring. Okay, so this is clear for you. Now we can do some numericals based on it, right? So before that, one more thing I want to add. So we have discussed the Van Hoff factor and all right. So as the Van Hoff factor is an important parameter, definitely there will be changes in the colligative property. So we can calculate the colligative property that is for relative lowering of vapor pressure. It will be delta P divided by P naught is equal to I, the Van Hoff factor, into mole fraction of solute. And for the elevation of boiling point, delta TF is equal to I into a cryoscopic constant Kf into molality. And for this is for the freezing point depression, sorry, elevation and boiling point, delta TB is equal to I into molar elevation constant or ebullioscopic constant into molality. And for osmotic pressure, pi is equal to I, Van Hoff factor I into molarity into R into T. So this is the changes in the colligative property. So we have to consider the I value also. So when there is dissociation, what will happen? There will be an increase in the colligative property because it's directly proportional, right? For association, the I value is lesser, so there will be decrease, right? Now we can solve the numericals based on it. See here, 3.9 gram of benzoic acid dissolved in 49 gram of benzene shows a depression in freezing point of 1.62. Here we are adding the benzoic acid, which is an electrolyte, and when you are adding it in benzene, definitely there will be association or dissociation will occur. Okay, and it shows a depression in freezing point of 1.62 Kelvin. Calculate the Van Hoff factor and predict the nature of the solute. That means whether the solute get associated or the solute get dissociated, and you are provided with the molar mass of benzoic acid as 122 gram per mole and the cryoscopic constant Kf for the benzene as 4.9 Kelvin kilogram per mole. Now let's see how we will solve this problem. See here the mass of solute. Mass of solute, it is given 3.9 and the molar mass of solute is given 122. So we can easily find out the number of moles of solute, right? Number of moles of solute is equal to 3.9 divided by 122, right? And the mass of solvent, it is given, the mass of solvent is equal to what? 49 gram. That means it is equal to 0.049 kilogram. So you can calculate the molality here. Number of moles of solute is given and the mass of solvent, it is given 3.9 upon 122 into 0.049. So when you are doing this calculation, you will get the value 0.65 molar. That is the molality of solution. Now the depression in the freezing point, that is delta PF value, it is given 1.62 and also the KF value is also given. It is KF value is 4.9 Kelvin kilogram per mole. Okay. Now see what is delta TF. Delta TF is equal to I into KF into molality, right? So all the values are given here. You can easily find out the I value. If the Van Hoff factor value is greater than 1, it means the solute is dissociating. If I value is less than 1, it means the solute is associating, right? So when you substitute the value 1.62 is equal to I into 4.9 into 0.65. So after doing the calculation, you will get the I value, and if the I value is greater than 1, it indicates it is dissociating. If it is I value is less than 1, it indicates it is associating. Just find out the solution and see and put in comment box whether it is association or dissociation. Okay. Now we can see the another problem. That is also 2 gram of benzoic acid is dissolving in 25 gram of benzene, and it shows a depression in freezing point equal to 1.62, and the molar depression constant, nothing but the cryoscopic constant, it is given as 4.9 Kelvin kilogram per mole. And what is the percentage association of acid if it forms a dimer in solution? So what you want to find out is the percentage association, and it is given that it forms a dimer. Okay. So what we want to do here? Here the mass is given, and also the mass of the solvent is given, and you know the molar mass of the solute. So we can find out the I value from there, right? The same method that we did for here, we can find out the I value. And for the association, what the value percentage I is equal to N into 1 minus I divided by N minus 1, right? So after substituting the values, you can easily find out the percentage of association, right? So here already, we have done the same model of calculation. The previous question, the same model what we did, and we want to just to find out the I value. After getting the I value, put the substitution here. You will get the answer. Here, what will be the N value? Since it is forming a dimer, it will be, N will be 2, right? So, by substituting the values, you can easily solve problem. Okay? Now, let's see the next question. That is, give the reason for red blood cells, that is RBC, shrink when placed in saline water but swells in distilled water. See how easy it is. If you take the saline water, okay, we are taking the saline water, or also we are taking a distilled water. We are taking the distilled water. If you put the red blood cells in the saline water and in the distilled water, here saline water means it's a hypertonic solution, right? So the solvent, what will happen? The water will come out from the cell to the solution. That will cause the cell to shrink, right? So here the osmotic pressure, the fluid inside this cell is, so the fluid inside the cell is low concentration. Here it is high concentration. So the solvent will move from the low concentration to high concentration. That causes the cell to shrink. That is the reason if you put in a saline water, the cell will shrink, because the concentration is more for the saline water and the fluid inside the cell have a low concentration. So the solvent will move from the low concentration to high concentration through the semi-permeable membrane, that is the cell membrane, which will cause the cell to shrink. At the same time, if you are putting in the distilled water, this is the low concentration solution, distilled water, and the fluid inside the cell is high concentration. So, what will happen? The fluid will move from solution inside the cell. So, what will happen? The cell will swell. That is what happened when you put the red blood cells in the distilled water. The cell get swells up, right? So, if you know the concept, you could easily answer for this kind of questions. So, now see the last question, that is, give the reason for the following. Measurement of osmotic pressure method is preferred for the determination of molar masses of macromolecules such as proteins and polymers. We have done that. We will be using the colligative property methods for measuring the molar masses of the solute, right? So in that, why we are preferring the osmotic pressure method for the determination of molecular masses of proteins and polymers. What may be the reason? Because the osmotic pressure we are measuring in the normal room temperature, right? But at all the other are we are doing at elevated temperature. What's the nature of the proteins and the polymers? They will get denatured or their nature will be getting changed at a high temperature. So if we are opting the osmotic pressure method, which is carrying out at a room temperature, so it won't affect the nature or it will not cause the denaturation of the proteins and polymers. That is why we will always prefer the osmotic pressure method for determining the molar masses of proteins and polymers. And also, if you are using the elevation in boiling point, depression in freezing point, or relative lowering of vapor pressure, they will get a very low value. It will be difficult to measure the value accurately. But at the same time, the osmotic pressure value will give you the exact value at a very low concentration also. That is the reason why we are using the osmotic pressure. The major thing is it is carrying out at room temperature, and if you are using the osmotic pressure method, we will get exact values, right? Now, the second question is, aquatic animals are more comfortable in cold water than in warm water. What may be the reason? What you learned? The solubility of gas is more at lower temperature, right? As the temperature increases, the solubility of gas decreases, isn't it? So, in cold water, there will be more dissolved oxygen. So, the aquatic animals will be feeling more comfortable because they are getting enough oxygen there. But at the same time, in warm water, the temperature is slightly higher. So, the amount of the dissolved oxygen will be lesser. Okay, so there will be discomfort for the aquatic animals in warm water, but at the same time they are more comfortable in the cold water because there will be more dissolved oxygen in it, right? Now, the last question, it's based on whatever the topic that we discussed today. That's elevation of boiling point of 1 molar KCl solution is nearly double than that of 1 molar sugar solution. Why? Here both have the same concentration, 1 molar KCl and a 1 molar sugar solution. But sugar is a non-electrolyte. It won't undergo the association or dissociation. But at the same time, the KCl is an electrolyte. It will undergo dissociation. If it undergo dissociation means KCl is dissociating, it will be dissociating to give 2 moles of K plus and the Cl minus. So, there the I value will be 2 by 1, that is equal to 2. So, as the I is 2, what is the elevation in boiling point? Delta TB is equal to I into Kb into molarity. If it is twice means definitely the elevation in boiling point will be getting doubled. But at the same time, here there is no association or dissociation. So the I value will be 1. Right? So delta TB is equal to Kb into M. So here I is 2. So there is double amount of doubling the elevation and the boiling point. Isn't it? So I hope this is clear for you. So, with this question, I am winding up the session and we have completed the solution chapter entirely, and we have discussed in this particular chapter, from this 4 parts of the video, we have discussed the different methods of expressing the concentration of solution, and in the next part we discussed about the Henry's law and Rawls law. In Rawls law we discussed about the ideal solution and non-ideal solution, that is the solutions which obey the Rawls law and the solutions which do not obey the Rawls law. And in non-ideal solution there are 2 categories we learned: positive deviation from Rawls law and negative deviation from Rawls law. And also we discussed about the azeotrops, high boiling azeotrops and minimum boiling and maximum boiling, not high boiling, minimum boiling and maximum boiling azeotrops we discussed, right? And also the colligative properties, that is the relative lowering of vapor pressure, depression in freezing point, elevation in boiling point, as well as the osmotic pressure. And in today's session, we have discussed the reverse osmosis as well as isotonic, hypertonic and hypotonic solution, and also the abnormal molar mass and Van Hoff factor. I hope all these are clear for you. Do preparing for your board exam well, and your Nandini ma'am will be coming with the electromagnetic induction chapter on 21st November, Tuesday. So stay tuned with us. Thank you.